This is the applications of Bayet and Savart law. And the first applications of Bayet-Savart law is to find the magnetic field at the center of a circular current loop. Okay, so this is my circular current loop which carries a current I in the clockwise direction. Okay, so this is a current I, it is flowing in this way. Now, my aim is to find the magnetic field at the center. Suppose this point O is the center of the loop. Now I want to find how much is the magnetic field at the center of this loop. So for that, I will divide this whole loop into small current element. So one such small current element, it is this one, where the current over this element, it is I, and this element, let's say it is having a length dl. Okay, all right. So the radius of the loop, that is r, rho. This radius of the loop, it makes an angle how much with respect to dl. So the angle here, it is 90 degree, which means theta is 90 degree. Okay, so in order to find the magnetic field at this center due to this whole circular loop, first I will find out the magnetic field dB, small magnetic field dB at the center of the loop due to this current element dl. So for that, we will use Bayet and Savart, which says the magnetic field due to a current element IDL is equals to mu naught upon 4 pi I dl sine theta upon r square. But theta in this case is 90 degree. So in place of theta, I will write sine 90, okay, upon r square. But we know sine 90 degree is 1. So therefore this is 1. So 1 times IDL will be just equals to IDL. So this is my equation number 1. Okay. Now, this is just the magnitude of a small magnetic field at this center due to this current element IDL. Now we shall see about the directions of this small magnetic field dB at the center. Where is the directions of this small dB at this center? The directions of this small current, of this small magnetic field at the center, it is actually perpendicular to the plane and it is directed inward. At this center, you know this dB, it is perpendicular to this plane and it is going inward towards the plane of the boat. Okay, how do we know that? So, right, we can determine about the directions of the magnetic field at the center of the circular loop by applying one rule which we call a right hand palm rule. So if you stretch your fingers like this is your thumb, and call your fingers in this way. So if the call fingers represents the direction, right? If the call fingers represent the directions of the current, so current is going in this way. So this extended thumb, which is pointing towards the boat, this will give you the directions of the magnetic field at the center of the loop. Okay, so now this directions of dB and the magnitude as well, it is equals to this much, and this magnitude and the directions of this magnetic field, it is not just from this current element, from this one current element. You can have a current element over here also. So over here, right, the directions between this radius and the element dl also is 90 degree. And the direction, it is at the center, the directions of this dB is always pointing, right, inwards, perpendicular to the plane of the loop. So therefore, right, the contribution of all these current element to the magnetic field at the center, it is same. Okay, and the direction is always perpendicular to the plane of the loop. So therefore, in order to get or to find the magnetic field at the center of the loop due to this whole current element, then I will integrate this equation to 1. So by integrating this equation to 1, you will get integrations of dB, let's say from 0 to b, is equals to integration of mu naught upon 4 pi I dl upon r square. And the limits of integration in this case, it is actually for the let's say for the circumference, because here, right, you start from this point and you're going along the circumference in this way. So that means you have to integrate, right, because the small dl in this case, it is taking along the circumference. So therefore the limits of integrations for the right hand side, it should vary from 0 till the radius, sorry, till 2 pi r, because we know the circumference of a circle is 2 pi r. What is integrations of dB? Integrations of dB is b, and the limit is from 0 to b. So when you substitute the upper limit and the lower limit, again you'll get b. This mu naught upon 4 pi, it is a constant quantity. I, the current which is passing through the loop, is constant. This radius of the loop also is constant. I'll take it out. So inside integrations, I'll have only integrations from left to right over dl. Now, this magnetic field at the center of the loop, it can be now written as mu naught upon 4 pi I upon r square. What is this integrations of dl? We know integrations of dx is x, so integrations of dl will be l. And the limit is from 0 to 2 pi r. Okay. Again, the magnetic field at the center of the loop, it can't be further written as mu naught upon 4 pi I upon r square. Okay, if you substitute the upper limit for L, it is 2 pi r, and then you minus by substituting the lower limits of L, which is 0. So B here will be equals to mu naught upon 4 pi I upon r square times 2 pi r. So this pi and this pi cancel, this r with this square cancel, this 2 with this 4 cancel, you get 2 here. So therefore the magnetic field at the center of the current carrying circular loop is equals to mu naught I upon 2r. Okay, so this is how we find the magnitude of the magnetic field at the center of the circular loop carrying a current I. So please do study well about this topic. This is very important. It may ask you again in exams about this derivation.